dear student, let us begin the lectures on machine design part 1. This is lecture number 36 and the topic is design of cylinders and pressure vessels. Now, this is the first part of the lectures on the same topic. Now, cylinders and pressure vessels, they are one of the very important components of modern day machines. There are number of equipments used in machines which are made in the shape of cylinders and they contain liquid or gas with high pressure. So, it is very important to design them properly because as I said they contain pressurized liquid. Sometimes they may be chemicals which are toxic in nature. So, a failure of such component leads to disaster, that may be the loss of life, property and many other things. So, the design of cylinders and pressure vessels is very important. Now, we are going to begin the discussion. Now, first the classification of cylinders. Now, cylinders cylinders they are very well known, that is, this is the cross section of a cylinder. If you look at here, so this is the internal diameter di and this is the external do, and this distance is the thickness T. Definitely T will be equal to do minus di divided by 2. Now, cylinders are classified according to various criteria. One is according to the thickness. Now, if this T, that is the thickness of the cylinder, is much small compared to that of di, that is T is very much small compared to di, then we call this to be thin cylinders. Now, how much small? Then the practice is T by di must be less than 0.1. So, the thickness of the cylinder, if it is lesser than 10% of the internal diameter, then we call this to be thin cylinder. Then if this is not satisfied, that is T is sufficiently thick, then we call it a thick cylinders. Now, in this class we are going to discuss the thin cylinders. Remember, in the thin cylinders the thickness is very small. So, according to end constructions, now there is another way of classifying the same cylinder. One is the closed ended. Sometimes we have the cylinders which are closed ended. So, the cylinders will have this kind of cap which may be either integral part of it or they may be screwed or riveted, that is joined. Then this is the closed ended cylinder. Various examples are boilers, then pressure vessels normally which you see in a chemical factory, they contain high pressurized liquid. So, these are to be closed ended. Then there are open ended cylinders. When this ending, that is these are not present, then we call it open ended cylinder, and the examples are the cylinders used in the IC engine, the piston cylinder assembly, then the cylinder is normally open ended cylinder. So, here we are going to discuss thin cylinders. Now, what are the stresses in a cylindrical pressure vessels? Now, here we have a pressure vessel which is again we consider thin, this is always. Then this is a pressure vessel which has thickness very small compared to the diameter. This may be open ended or closed ended. Let us take it to be closed ended, and inside it there is fluid, so which has pressure uniform throughout. Let us take that the pressure is P. throughout. Now, here this is the cylinder, the thickness is, let us consider to be T. Now, remember we are going to consider the cylindrical pressure vessels, that means that we are going to only consider up to this portion, the stresses within this region. Now, what are the different stresses appearing here? You will see that there are two kinds of stresses. The first is that if you just make a line here and cut it into two halves, then how do you see? Then there will be one part of the cylinder and then pressure is acting over here, and there are stresses. So, again on the same surface there will be stresses. Now, this stress, this is called as tangential stress or hoop stress, denoted by sigma h. Now, if you balance the force, then what you get is that sigma h times the total area of cross section on which it is acting, that is twice of this length, that is sigma h times twice of this length, twice L times the thickness. This is the area over which sigma h is acting, and this is balanced by the total force acting upwards is the projected area, which will be equal to twice R. Now, R I or R, here of course we take R I, but remember if T is very small compared to R I, then it is same as taking the average radius, which is R I plus R O divided by 2, which is roughly equal to either R I or R O. So, this total area is twice R I times L and the pressure P, which if you calculate, then you get sigma h will be equal to P R by T. So, this is the hoop stress and that acts along the tangential or the circumferential directions. If you had taken a cut somewhere here, then of course, the stress would have been same. Now, here what one sees from this figure, that this is axially symmetric. What is meant by axially symmetric? Of course, if you look from any side whatsoever, you will see the same object, and since the loading is also axially symmetric, that is it is uniform throughout, then if you cut along any plane, not necessarily along this plane, but along any plane diametrically opposite, if you take a diametrical cut, then of course, you will get the same distribution. So, which means that sigma h is constant throughout the circumference. So, at every point you will have the same sigma h. What is the other form of stress? Now, this is the hoop stress. Now, we have other forms of stress as well, that is visible if you take a different cut. Now, if you cut from this point, so that is if you take a cut over here, then what you see that there is a portion of the cylinder which is of course looks like this, then pressure acts throughout, here is the P, and again sigma acts over here, and this is now longitudinal, which is denoted by sigma L. Now, if you balance the force, then what you get is that sigma L times the area will be twice pi R times T, and that is equal to, so this is the area of cross section of this particular sections, and that will be equal to the net force due to the pressures, which is pi R square times P. Now, if you make these calculations, then you will get P sigma L equal to P r by twice T. Now, remember this is the longitudinal stress. So, it is same throughout this region. So, you will have two stresses, one is sigma h. Remember, if you use the formula, then this is nothing but sigma h divided by 2, because we have already seen that sigma h is nothing but P r by T. Now, what we see that the hoop stress is double that of the longitudinal stress. So, therefore, the failure will take place, if at all it fails, then the failure will take place in any of these longitudinal sections. So, one has to be very careful in designing that. Sometimes now here, because of manufacturing, what we have is that this is made not as a continuous section, but by different joints. So, you will come across different kinds of joints. Now, here a typical cylindrical vessel, and it may be made of two parts like this. Now, there are two sheets which are welded here or riveted here, and then there is joint here. Sometimes we have a different configuration, maybe something like this. So, in any case, you will see lots of joints are there. Now, when we have talked of the joints, then we talked of the joint efficiency. That is, although this is theoretically this comes from the theoretical calculations, these kinds of stresses, but because of this joint, the member gets weakened. So, its ability to take that much load is no more there. So, we will have to consider the efficiency of the joint, and if you take the efficiency into consideration, then of course, the stress developed will be equal to sigma h is P r by T, and of course, here we will have to multiply by one efficiency. Similarly, for sigma L equal to P r by twice T, and we will have to again multiply by the efficiency. Now, how to design that? Then the design criteria is that suppose there may be various design criteria, we select for particular P and then want to find out what is the value of T. Now, T will be equal to of course P r divided by sigma, and here sigma h is the maximum stress. So, this is divided by eta. So, this will govern the design, because this has maximum stress, the failure probability is greater over here. And now, sigma h is again the allowable stress. So, once we know the allowable stress, then we can design for what is the value of T. In some cases, we have to give some allowance over here. So, here we have to add some values. Now, what is the purpose of this additions? Remember, these tubes or these shells contains the chemicals. So, there are corrosions possible. Now, in order to take care of this corrosions, then we will have to add some extra thickness, because some material will be corroded, and after corrosions, that is when this extra material is gone, then the remaining material should be able to withstand that particular pressure P. Sometimes of course, we have to give this C, because we need to rebore the cylinders. For example, in the piston, cylinder pistons, whenever the piston rubs along the cylinder surface, then wear and tear takes place. So, from time to time, at least after a number of cycle, we have to rebore the cylinder hole, because otherwise the engine efficiency or the cylinder efficiency will go down. So, therefore, in order to provide this give a provisions for this reboring, we keep this C. Now, normally in the piston cylinder we give an allowance of 6 to 12 millimeter. Again this will be found in different codes. Now, these are about the stresses. Sometimes of course, now here these are the normal stresses you see. Now, if you look at any element, then what you have, that if you look at any element, so there are two stresses, one is sigma h and another is sigma L and sigma L. Now, these are the normal stresses. Now, here although I did not mention, but here the assumptions, basic assumption is deriving this equation is that there is no sigma r, that is this radial stress is 0. Now, what we see is that although there is pressure inside, that is if you have a cylinder, then pressure is inside throughout, then the inner surface will have sigma r is equal to minus p. That is very clear, because the stress over here on the inner surface will be equal to minus p. On the outer surface on the other hand, it will be 0. So, there will be variations from minus p to 0. Now, if you have a very thin cylinder, then what will be the order of sigma h? This is p times r by t. Now, if r is much larger than t, then what we get? We get sigma h is much larger than p. So, therefore, whatever may be the variations, so definitely within it, it will be something between p and 0, and this after within this, so this is p and 0, and therefore, sigma h will be much larger than p. Therefore, it is safe now to neglect this sigma r, and we have only used the force conditions, that is the equilibrium equations, neglecting any sigma r. So, therefore, these are the two normal stresses, and then if we consider the maximum shear stress, then it is easy to see that if we draw the Mohr circle, then sigma h is double that of sigma L. So, this is sigma L and this is sigma h. So, if you draw a Mohr circle, then this is the circle. So, therefore, the maximum shear stress is nothing but this point, which is equal to tau max equal to sigma h minus sigma L divided by 2, which is the radius of this Mohr circle. But now, you have to remember one thing, that is this is the maximum stress in this plane of applications of, or the in the plane of the of sigma L and sigma h, but this is not the maximum shear stress overall, because in the, so in if you take the 3-dimensional figure, then the normal stresses are sigma L and sigma h, but here the normal stress is 0. So, then if you consider the 3-dimensional case, then what you get is that there are three such Mohr circle. One is here, there is another circle, that is and the maximum stress, maximum shear stress tau max is not sigma h minus sigma L by 2, but it is nothing but sigma h divided by 2, and this occurs in a different plane. This occurs only in this particular plane, the maximum shear stress. whereas we have earlier we have considered only in the sigma L sigma H plane, but now the maximum shear stress occurs in that particular plane. So, this is very important while designing, because sometimes the material may fail due to shear, and we have to design the pressure vessel such that the shear stress goes below certain limit. So, then we have to consider for this maximum shear stress, which is not sigma H minus sigma L by 2, but sigma H by 2. So, this is very important. Now, here we have learned something about the stresses in a cylindrical pressure vessels. Now, let us move along. Now, design of thin boiler tubes. This pressure vessels, that is boilers, they contain the tube, and those tubes are to be designed according to some formula. We consult some design code, and the most popular code is ASME boiler and pressure vessel design code. Now, here we see that the permissible steam pressures, now in that code all sorts of data are given. Now, these are updated from time to time, but what we see here, this representative is permissible steam pressure in steel pipe. Now, in boilers there may be steam or maybe water tube, then the tubes may be steel or wrought iron, etc. Then this maximum permissible steam pressure is twice sigma H minus 0.165 divided by D0 minus 8.78. Now, this is in kg force per centimeter square. Remember, this is nothing but 0.1 megapascal. So, if you want to find out in megapascal, then you will have to multiply this by 0.1, and H and D, these are of course in centimeter, this is in centimeter. Now, this formula is valid only for D0, which is quite small, that is between 6.35 millimeter to 12.7 millimeter. So, it is about quarter inch to half inch. Now, if you go for D0 more than half inch, then what we see, P is equal to twice sigma H minus 0.254 divided by D0, again this is kg force per centimeter square. Now, when we have pressure in steel tubes for water tube boiler, when we have water tube boiler, then we have this formula, that is P is sigma H minus 0.1 divided by D0 minus C. Now, here we see that this sigma and C, these are constants, and they depend upon different types of joints and materials. As I said, that the tubes may be steel or of cast or of wrought iron, and of wrought iron there may be the welded joints or in the continuous seamless tube. So, depending upon the type of joint, welded joints, again the most popular is the lap welding. So, if the joint has lap welding, then we have different sigma and of course, C different than the tube made of steel and seamless tube, and then also that depends upon the maximum pressure limits. So, everything is given in the code itself, but what I wanted to show that the boiler tubes also could be designed with this help of the pressure vessel theories, but of course, we have to use some empirical formula if we want to design safe. Now, we come to another thing, that is the stresses in axially symmetric pressure vessels. Now, there are various kinds of axially symmetric pressure vessels. There may be pressure vessels like this. For example, this is one axially symmetric pressure vessel of joint of various sections. Now, this is axially symmetric. If you have joints, so it will look very much same throughout. So, this is axially symmetric. And then maybe of course, cylindrical, as I have shown already, cylindrical, which is again axially symmetric. So, what are the properties of axially symmetric pressure vessels? Here the axially symmetric means that if you look from any side up to 2 pi angle, then it will look the same, but this is about the geometry. But in order to be this axially symmetric system, the loading has to be also axially symmetric. So, if you consider this to be in the wind loaded, suppose you consider such a very tall such cylinder. Now, we consider wind load here from one side, then say this is wind, then this is not axially symmetric. So, this is not axisymmetric because the loading is from one side. But if the loading is from all sides, then of course, we may call it the if the loading is of course same from all sides, then we call it axisymmetric system. So, there are two things which are important. One is that the geometry is axisymmetric, it has to look the same from whatever angle you look at, and secondly, so first is that geometry and second is loading. So, if both of them are axisymmetric, then we may call it the axisymmetric pressure vessels, axisymmetric systems. Now, here we consider the such kind of pressure vessels which contain liquid and or gas which exerts a uniform pressure throughout. Definitely the loading is uniform, that is, if you look from any side we can have the same type of loading. So, therefore, loading is axisymmetric, geometry is axisymmetric, and this is axisymmetric pressure vessels. Here we want to consider the different stresses in such axisymmetric pressure vessels. So, let us take up that. Now, in axisymmetric pressure vessels there are let us look at the geometry of such axisymmetric pressure vessels. If you consider one such part of the axisymmetric pressure vessel which is not spherical, not yes. So, something like this, then we can have two principal radii. One is that, so this is axisymmetric, therefore, if you look from any side it will look the same, and it is formed by rotating this line, rotating this kind of parabolic line about this axis, and you will find this axisymmetric profile. Now, any point will have two principal curvatures. One is that here if you consider this particular point, let us say A, then this is the normal to this point goes here. So, this could be taken to be a part of the circle, whose radius is, let us say, is called R m, and this is called the meridional radius. So, there are two radii, one is meridional radius, one is tangential radius. Now, the tangential radius, what happens? Now, there will be another circle which could be drawn on this point. Now, one is along this side, another is along that side. So, the radius of this is of course will be here, because it has to be same throughout. One can have the similar point here, and it will have the same radii. So, this will have another radii, and this is R t. So, we have two kinds of radii, one is R m, this is meridional radius, that is radius along the meridian, and this is R t. Definitely R t is most of the time R t is smaller than R m. Now, here we use the membrane theory. Now, this is about the geometry of such pressure vessels. If you use the membrane theory, now membrane theory again assumes the same thing, that is we neglect the stress distributions along the thickness of the plate. That is, the thickness of the plate is so small compared to the other dimensions, that is the stress variations normal to the directions of this or along of the plate or along the thickness of the plate is very small, or the stress is very small compared to the other stresses. So, if you use those assumptions, then we can go for the analysis. If you consider a small portion, then of course so if you consider a very small portion which has of course thickness T, let us say. So, this is the thickness. Now, here of course we have two radii, one is this meridional radii R m and another is the R T. Now, what are the stresses acting over here? The stresses are here sigma T and this is sigma m. Similarly, here acts sigma T on the other side of the surface and here sigma m. So, there are 4 stresses and the pressure is acting throughout. So, pressure is acting over here and which has uniform distributions P. Now, if you balance the forces along the radial directions, then we get one equations, that is the total force here. If you consider this length to be, this is of delta theta and that delta phi. So, this is delta theta and that is delta phi, then the total force on it will be sigma m times this area of cross section, which is equal to R T times delta phi times T. So, this is the area of cross section and of course, this is now curved. So, therefore, if you consider this to be one circle, then what you see is that sigma m is acting over here, sigma m is acting over here. So, the total, so this angle is roughly almost delta theta by 2. So, the total component along the radial direction is sin delta theta by 2 plus of course, we have the other component, that is sigma t, again R m delta theta t times twice sin delta phi divided by 2, again due to the same considerations, and that will be equal to P, and the total area over which P is acting, this will be R m times R t delta theta times delta phi. So, this is now the expression. Now, if we consider that this is infinitesimally small area. So, therefore, this is very small, that is very small. So, sin theta by 2 is almost equal to sin delta theta by 2 is delta theta by 2. Now, what we can do, we can replace here this divided by. So, sin is almost equal to sin of theta is theta again here, and if you use then, now once you consider these expressions, then what you get after some algebraic manipulations, this following form, that is sigma m divided by R m plus sigma t divided by R t is equal to P by T. So, this is one expression relating sigma m, sigma t, P, R m, R t and T. Now, how to get the other expressions? Now, remember, if you consider the other cross section, the longitudinal cross section, that is, if you have a cylinder here, you take a cut across here. So, therefore, what you have is the sigma m acting over here, sigma m is acting over there, and what is the expressions now here? Of course, the radius is r, and remember this radius, this is r t. Now, this angle is again theta. If this is called theta, then this is also theta. So, therefore, the total force balance will be equal to sigma m, and the surface area over which it is acting is twice pi r times t, and this is only the cosine component will act. Now, remember the force is, pressure is acting throughout here. So, we are calculating the vertical component of sigma m. So, this is equal to, this is cosine theta, and that will be equal to pi p times pi r square. So, therefore, what we get is this expression, that is sigma m. Now, remember, if you write that, then you get sigma m equal to P r by t, and this is divided by twice, and this is cosine theta, and r divided by cosine theta is nothing but r t. So, P r t by twice t. Now, remember what we had in case of cylindrical pressure vessels, then of course, r t is nothing but r. Now, the area, because this theta is always 0 degree. So, therefore, r t is nothing but r, and in that case sigma m, that is the meridional stress which we called as longitudinal stress, is nothing but P r by 2 t. But here of course, we have P r t by 2 t when we have a general situations. Now, if you combine this again with the other form, then what we get is that sigma m by r m plus sigma t by r t is P by t. So, therefore, sigma m is given here. So, sigma t by r t will be equal to P by t times this is 2 twice minus r t by r m . So, this is clear, and then sigma t, if you take this here, then P r t divided by twice t, which is equal to sigma m. So, that means sigma t will be equal to sigma m times twice minus r t divided by r m. Now, remember in the cylindrical pressure vessel, of course, we had r t, but r m was infinite, because the meridional stress, remember the meridional stress is the meridional radius of curvature was infinite, because this was a straight line in the cylindrical surface. So, if you draw a circle, then the radius will be infinite. Therefore, r m is infinite for cylindrical vessels, and what we get is sigma t equal to twice sigma m, that is the tangential stress in the cylindrical pressure vessel it was called the hoop stress, which is equal to double that of sigma m. So, this is the general formula and we have verified that at least with our known theory. Now, let me write it down again. This is sigma m, which is equal to P R T divided by twice T, and sigma T is sigma m times 2 minus R T divided by R m. Now, in some vessels what we have is that suppose the cross section changes. Here see there is abrupt change. So, there is an abrupt change over here. Now, what we see that R T, so that is this tangential radius, it changes gradually. So, if you draw this R T, then you will see that the R T at this point, whether you look from this side or that side, that will be same. So, therefore, if there is a discontinuity in cross sections, that is the geometrical discontinuity, then sigma m is continuous. That is the sigma m, if you consider the sigma m at any point 1, which is, suppose this is called 1 and 1, and sigma m at any point which is lying on this at 1, that is very near to 1, which is lying on this surface, and if you consider sigma m again very near to 1 lying on this particular surface, then we see a gradual change. That is, there will be no discontinuity in sigma m if you go from this side to that side. But sigma t here, because R m is changing, if you see the R m here, of course, if there is a change, then R m will be changing, and therefore, we get sigma t. Of course, it is not visible from this, but had we had one continuous curve which has changed this curvature over here, then we had sigma t, which is equal to sigma m times twice minus R T divided by R m, and because a change in R m, we had a sharp discontinuity in sigma t. So, in case of such cylinders, sigma m will be continuous, whereas there will be a sharp change in sigma t. So, therefore, when there is a sharp change in sigma t, there will be stress concentrations. So, this part, what is important is that in this zone where the geometry changes, sigma t will have a sharp change and will have a stress concentrations in the circumferential directions. That is very important, because we had to give enough reinforcement, that is, we have to give much care in order to design this particular part of this pressure vessels. So, that is what we had to say from this axisymmetric pressure vessel theory. Now, let us come to the next case, that is the pressure vessels heads and their design. Now, the pressure vessels, when of course, there is no, this is open ended pressure vessel or open ended cylinder, then we cannot talk of any head, but pressure vessels are, of course, as the name applies, that it has to contain some chemicals or some fluid at high pressures. So, we need enclosure from all sides. So, we need to design head. Now, there are various kinds of heads available. You see, the most widely used heads is called the disc end, and again this is the disc head. Now, this cannot be said to be spherical or hemispherical or any other shape, but it has a continuous change in curvature. So, therefore, this is complicated. If you want to describe it analytically, then it will have a very complicated equations, but this is called the disc head and they are connected again to the cylinder, maybe here by riveted joints, that is we have the cylinder here and we have a disc end here and we apply a rivet joint. So, this is one way of constructing the disc head. Also, we sometimes had the integral disc head where this is welded, that is here this is the cylinder and this is disc head and we have sometimes welding over here. So, this is welded joint. So, these are usual disc head. Now, there are other heads, for example, flat heads. Flat heads which may be so this is flat head and there are bolts . Bolted joints. So, this is one such flat head. We have a complicated structure in the head. For example, if you look at this section, then here the thickness is something which normally the disc head will have larger thickness. So, therefore, there is a gradual change in thickness from this side to that side and this is called the knuckle point. So, this is again disc head, but here this thickness is T1 and this is let us say T. Now, there is a radius R, this radius is very important in order to reduce the stresses, that is there is a there may be a stress concentration here. Now, how to design this pressure vessel heads? Now, pressure vessel heads are normally designed in plates and shell theory, that is we use the plate theory. Now, again when we have a cylindrical disc which is this kind of head, then the decision of thickness, that is design of this thickness, will depend on not only on the type of loading. So, there may be loading which is continuous uniform throughout, or there may be loading which is centrally acting, that is there may be a central load or uniform distributed load. So, depending upon the type of loading, of course, the deflection will be different and hence the stresses will be different. Again also this depends on how you fix it. So, there may be a situations when this is integrally connected, then of course, we will have to have a different boundary conditions. Remember when we talk of the displacement of a or the stresses within a plate, then we have to also consider the boundary conditions. So, there may be different boundary conditions. It may be, if this is bolted, then it will have different boundary conditions. If it is welded, then it will have different boundary conditions. So, this is to be defined, this is to be designed according to plate theory. Now, those are again tabulated. There are various literature available on the plate theory, and normally in a design handbook you will see different kinds of figures, and depending upon the loads etc., we will have the different dimensions. So, the most important dimension is this thickness, which is to be selected from the from this theory, that is, if you look at the table, then you will be able to select that. But let us now consider a few things which are of interest in this head design. That is, as I said, that whenever there is a change in the, so this is the disc end, and this is the cylinder. Now, here as we have discussed that sigma m, here of course the longitudinal stress, and here again the sigma m, this changes continuously, but in case of sigma t it changes abruptly, that is the sigma t here and sigma t there will have two different values. So, this is quite important, because then we will have to make adequate reinforcement, that is, here of course the tendency is that there will be a stress concentration. Another point is important, that is, we have a pressure throughout. Remember, this is pressure vessel. So, we had pressure acting throughout, and because of this pressure, then this will try to the cylinder size will try to change, that is, when we have a cylinder which is subjected to internal pressure, then its radius will change, gradually it will increase. Now, if we consider this increment in this size, in this area and in that area, then there will be the differential increment, that is, this part will increase, let us say up to this point, and this will increase up to some other point. So, there will be a bending here. So, now what happens is that this after deformation the shape looks like something like this. So, there will be a bending. So, that is very important to consider this bending. Again, sigma t here in this side, in these portions, sigma t will be generally compressive. So, whenever we have a cylindrical shell and this end, this is the plate, this is the head. So, here of course, sigma t is compressive in nature. Therefore, what may happen, the buckling may take place here because it is now subjected to compressions. So, it may buckle, right, everything this buckle. So, buckling may take place in this cap. So, these are the things which are to be taken into account. Now, these are the issues for the pressure vessel heads and their design. Now, let us go to this particular slide, which says the relevant codes for pressure vessel design. Now, here pressure vessel are very important and we have to be very careful in designing. So, instead of using different formulas, we stick to different codes. One such very important codes and widely used codes is from the ASME, and it says the ASME boiler and pressure vessel code. Now, this code gets modified from time to time, and each year there will be some addendum, some dedendum, and we will have to consider the latest. And whenever we design something, we will have to stick to one particular code. We cannot change from one code to the other code, because that may lead to disastrous failure. Now, this boiler and pressure vessel code is divided into 11 sections. So, there are 11 sections, but out of it mostly section 1 and section 8, these are of importance to the designer. Here the boilers, section 1 deals with the boilers, section 2 materials for pressure vessels, section 3 nuclear power plant components. Now, which is very important, and here of course, we will have to consider many other things. When we go for designing such components in nuclear power plants, then we will have to talk of the vibration problem and fatigue, that is variable loading problem, etc. All of them are very important, because we want to make this very reliable design. That is, whenever we have the nuclear power plant components, we cannot compromise with anything. So, therefore, we will have to check for different other things rather than static loading in order to make the design safe. Now, section 8, it deals with the pressure vessels. Now, again it is divided into two parts, one is lower stress and one is higher stress. For division 1, this is lower stress, and division 2, this is higher stress. Now, when you go to the higher stress, then a little modification may be there. Just give you an example, that is sigma H hoop stress is PR by T, I am sorry, PR by T. So, if you want to design, then T is PR divided by sigma allowable, and again we will have to multiply by that is divide by efficiency in order to get T. Now, this is very good for the lower stress. Now, if you go to higher stress, then this code says that you will have to multiply here by 0.6 P. Now, why these multiplications? Because at higher stress there will be plastic deformations. In order to make the design formula, the results from this design formula very similar to that from the plastic analysis, we subtract 0.6 times P here. So, this is given in the code itself, and we have to stick to that codes. Now, what I want to say is that this ASME boiler and pressure vessel code is very important, and if you want to design a pressure vessel, then you will have to stick to, you may stick to many such codes, but you will have to be consistent, and ASME boiler and pressure vessel code is very widely accepted code. Now, now we come to the end of this lecture. We have learned how to design a thin cylinders. We use the membrane theory, and we have then two kinds of stresses, one is meridional stress, one is the tangential stress, and they are of course related, as we have seen in the analysis. Now, meridional stresses, when the geometry changes, they remain continuous, but the tangential stresses, they change, and that leads to the stress concentrations, and this is to be again taken care of while designing. Now, in design, of course, we talked of the pressure, which is acting inside the cylinder, but there may be situation when pressure is external, then of course, the design modifications are to be made, and there are various formulas, for example, Professor Karman's formula, etc., which are used for that, and it may be crushed then, and one has to consider the crushing of the tube when the external pressure is applied, and those are again in the handbook. So, you will have to consult this handbook for various different specific applications. So, this is all for today's lectures. Thank you very much.